This is Jim Ledoux. I am on WDTD Storm of the Month webcast. We have Frank Lombardo and we have Zach Wienhoff. Both of them are going to talk about the degree of damage. This is the wind speed relationship in the Damage Assessment Toolkit, or the DAT, and its connection to engineering applications. They've done a careful examination of the database that we have for several damage indicators. They'll focus on one of them and talk about how they compare to some idealized models to see how we're doing as a weather service, and then showing how the usage of the DAT is being used in the research community. Frank Lombardo is an assistant professor at the University of Illinois, Urbana-Champaign. He was one of the lead authors in the NIST Joplin report. This was a Joplin report, and I'll tell you, this is like 450 pages after the event, looking at just about every aspect of the Joplin tornado of 2011. Zach Wienhoff is a forensics engineer and meteorologist at Haag Engineering. He just graduated from the University of Illinois and started up with Haag Engineering in the past year. So what I will do is go ahead and let Frank take this away.
Okay, thanks, Jim, and welcome everybody on the call. Good morning or good afternoon, depending on where you're at. And like Jim mentioned, we're going to talk about this DOD wind speed relationship in the DAT and its connection to engineering applications. So we'll start with kind of an introduction. This is probably not new information to everybody on the call, but if you kind of look at billion-dollar wind-related disasters in NOAA over the years, what you can see is one is that these events are increasing, and a large proportion are really due to severe storms and all the hazards that are associated with them. So as engineers looking at tornadoes specifically, we're really interested in the accurate estimation of all the tornado characteristics, whether it be intensity, frequency, or path dimensions for tornado risk estimation. But as most of you know, there are a lot of challenges in this kind of wind speed estimation and tornado characteristic estimation, and some of these have come out over the last 10 years or so. So one is obviously the dependability of the DOD wind speed ranges, all the challenges that a lot of you face when going out surveying. You might have a lot of tornado damage in your forecast area from multiple tornadoes, other job responsibilities and things similar to that, which make it difficult to go out and survey tornadoes. Some more recent research that has kind of served as additional motivation to us is showing that the frequency, intensity, and perhaps width is likely underestimated. And then again, Jim mentioned that I was involved in the NIST study, and what we found in that and FEMA after the 2011 tornadoes was that there are limitations really at the upper end of the EF scale, and the ratings tend to become more subjective. So to kind of further this motivation, we understand that there's really a large number of factors involved in the wind speed to damage relationship, and Zach will talk about quite a few of those. And really by extension, there's really large uncertainties and subjectivity kind of in this estimation process. And so a lot of the talk today will be geared to how do we quantify some of this uncertainty, and how can we look at different approaches to try to understand where these uncertainties are coming from. And so now I'll turn it over to Zach to talk a little bit more about some of the motivation behind this work.
As Frank mentioned, the focus of this work was to gain some perspective on some of the uncertainty and subjectivity, specifically in wind speed ratings. And of course, we're using the DAT to do that. But I want to take a step back first and kind of look at why some of these uncertainties exist. So just, kind of at the forefront, and obviously this has been extremely relevant over the last couple of days, and will continue to be the remainder of this week. But we know that structures protect people, and then tornadoes pose some of the greatest threats via extreme forces on these structures. So basically we have two schools of thought. Basically have a wind force and the resistance of the structure. So that the balance between those two, how much force is imparted on a structure, how much that structure is able to resist the load of the wind, will ultimately result in how much damage is sustained. And so I want to break this down because this is a thing I like to highlight a lot, is that when we say wind force versus structural resistance, oftentimes what gets lost is that we directly relate the wind speed to damage. And while obviously there's a strong correlation between these two, it's not exactly correct. More correctly, we would say that the wind speed is then related to a wind load, and then that wind load on a particular structure or object is related to how much damage is sustained. And so for a given wind speed, there's a wide range of potential outcomes given characteristics of the wind load, such as turbulence, content, duration of the load, etc. And one thing I want to highlight is that while there's a lot that we don't quite understand about all of these things, we know that tornado loading, thunderstorm wind loading, and hurricane loading are not equivalent. And so an outstanding question that kind of comes from this is how would damage generated by a tornado versus a straight line thunderstorm wind versus a hurricane wind compare to one another for the same maximum horizontal wind speed? Some things to sort of consider as the major factors that are associated with the wind loading and damage state of a particular structure. The first one is related to the wind and tornado characteristics, obviously. So what was the vertical wind component? We know in tornadoes compared to other extreme winds that the vertical wind component in tornadoes is not non-negligible. It is potentially significant in many or if not most cases. The atmospheric pressure change, how rapid the pressure changes as a tornado encounters a property. I know seeing a lot of tweets from the Weather Service in Norman on Sunday night, hearing about how their ears popped and things as the tornado moved over. Other things related to terrain impacts. This is particularly prevalent in the southeast, where we could have channeling of the flow and valleys and other impacts of terrain on tornadoes. Another big one is debris. Straight wind force on a building may do some degree of damage, but when we then impart debris into the flow and allow debris to impact the building envelope, how does that change the force on the building as well? The second factor is aerodynamics. So we need to consider the incident wind angle on the building, and then things like the building shape, the roof and structure shape. How do these things all affect the forces on different parts of the building and ultimately how the building will perform in the flow? And then the third one is related more to the structures. So obviously details like roof connections, wall connections, connections to the foundation, what sort of construction materials are used and things like that are all important when we consider these sorts of factors. So something I want to highlight is that going back to this wind load versus structural resistance, photos at the bottom right is an outlier structure, as we'll call it, from the Naperville, Illinois tornado in 2021. The structure was rated EF3. Obviously, you can see from the photo that there was significantly more damage to that particular building than those surrounding it. And so in many of the situations where we have outlier structures, survey of the particular building often leads to the conclusion that there was a lack of resistance, maybe poor construction, a construction defect, something about that building that made it more susceptible. But in a lot of these cases, and sort of adding to the uncertainty, is that comparatively, some of these buildings may sustain higher loading, especially in a case like a tornado where we may have subvortices. Things like configurations of streets and neighborhoods have been proven to affect these things. How the structure is oriented, where was the garage door in relation to the most intense flow? All of these things can be important in understanding how these situations evolve. And so obviously this is a talk examining how we use the damage assessment toolkit. And so again, we wanted to first gain some perspective on how these things are rated and kind of what the tendencies are to rate them. As Jim mentioned in the introduction, in this talk, we really only focused on DI2, the 1 and 2 family residences. This study could certainly be expanded to other DIs, but for this particular case, we're just focusing on those DIs alone. So the first thing we did is we went through, we had actually undertook this work a couple of years back, so the data set stopped in 2019, but our primary focus was looking at tornadoes that tended to have a longer track, had many DIs within the track that would allow us to get large samples, or as large samples of data as we could for some of these tornadoes. Most of them, for obvious reasons, ended up at EF2 plus tornadoes. And then I went through a bunch of these and looked at the EF rating, the DOD, the estimated wind speed that came from them, and then looked in detail where possible at some of the photographs and comments, and then the corresponding DOD and wind speeds that were assigned to each of them. The initial goal with all of this was to examine how individual survey teams and different survey teams across the country for different tornadoes might estimate wind speeds given a particular subset of damage and certain things they were seeing in the field, and then what the common assigned DODs were. One question that we found kind of interesting was that are there certain DODs that are more common? And so as you can see from in this panel at the bottom, one thing we found is that there was certain preference amongst DIs. Some of the DIs were plain and simple not as popular. So for example, DOD 3, broken windows, and DOD 5, where the structure shifts off the entire foundation, were not as commonly used as things like DOD 2, 4, 6, and 9. So that was one of the first things we noticed as we were moving forward. Splitting the DODs up and looking at them individually, we of course and unsurprisingly found that most of the wind speeds assigned to particular DODs were given at the expected value. But what we also did notice is that for some of the lower DODs, particularly DOD 4 and 6 here, you can see in the left and center columns, there was a tendency to rate those structures, give a wind speed higher than the expected value for the lower DOD. For upper DODs, I've shown only DOD 9 here, but there was a tendency to, of course, give a wind speed below the expected value. And so this was something interesting we found, and Frank will get more into this with the model results, but that was an initial observation that we made. And so then we also looked at DOD 10. Again, Frank will talk in more detail about this, but this also sort of underlines some of the subjectivity in this. So in looking at DOD 10, we found that from some of the photos and from some of the comments that were provided by the surveyors, we found multiple situations where the surveyor was suggesting that the damage state was sort of maximized for the 1 and 2 family residents. Yet there was a tendency for the wind speed estimates to vary quite substantially in some of these cases. So for example, in the Rochelle tornado, we had a DOD 10 from a well-constructed home swept clean, which was given an estimated wind speed of 200 miles an hour in EF4. Other cases, and like I said, I've only provided 2 here, but in this particular case, the DOD 10, even though it was sort of a maximum damage state, given an estimated wind speed of 190 miles an hour. So this was sort of our initial observations we made from pulling these data prior to kind of moving forward with modeling some of the results. And so now I'll turn it back over to Frank, and he can talk about how then we use these data to gain more perspective on this.
Thanks, Zach. So yeah, so Zach mentioned that we kind of looked at DI2 specifically and looked at each DOD and really tried to understand the DOD to wind speed relationship. And from the initial sample, what we found is that all DOD 10s that we sampled had estimated wind speeds of 200 miles per hour or less. So when it comes to the modeling part, we really wanted to get a more detailed sample at the higher end of both the tornado ratings and the DOD. And so we looked from 2008 to 2021 from EF4 and EF5 rated tornadoes. So we looked at some of the few EF5s that are in the DAT and kind of looked at the wind speed ratings for each of these DODs. So for example, in the bottom left there, EF4 tornadoes, DOD 9 rated homes, you can see a large proportion were rated at the expected value for DOD 9. They're 170 miles per hour. And so for EF4 tornadoes, DOD 10 rated homes, you can see again where it's kind of a bimodal distribution there where a lot were rated at 170 miles per hour and then another significant proportion right at 200. And then for EF5 rated tornadoes, which was a smaller subset, there just haven't been that many, haven't had one in almost 10 years now. For DOD 10 rated homes, for EF5 rated tornadoes, you can see the distribution changing, but the majority, almost all, were at either 200 miles per hour or 201 miles per hour, kind of looking at the individual wind speed estimates for these DOD 9 and DOD 10. And so the data in the DAT simply represents kind of a damage to wind speed relationship. And Zach showed some of the variability in the wind speed estimate for each DOD. And so in the modeling part, we'll talk about some broader questions that we're trying to answer with this data, is kind of build a kind of an empirical cumulative distribution function for each DOD. So for example, this is what this ECDF looks like for DOD 6. And you can see the majority of values are around the expected for DOD 6. And so what we can do is use some Monte Carlo simulation to generate a range of wind speeds for each DOD, which gives us some uncertainty measure or something that we can quantify in this relationship. And so key thing to remember here with not only the EF scale itself, but kind of this ECDF is that the simulated values don't exceed the bounds of the observed data. So, and these observed data are from the damage surveys that Zach mentioned. So for a given DOD, what we can do is simulate a wind speed based on these relationships. And so some initial observations, this is just on the DAT. So Zach kind of mentioned it. So we're kind of looking at it slightly differently here and looking at kind of how different DODs are rated, looking at the difference from the expected value. And so the first 2 findings are kind of what Zach mentioned, is that the lower DODs, for example, 2, 4, and 6, tend to be given an expected value or higher. So you can see, for example, DOD 2, there's only a small proportion of events that are rated lower than expected. 90+% are rated expected or higher. In higher DODs, things tend to be a little bit different. So for example, DOD 9, 80+% are rated either the expected value or lower. And so that's kind of a function of the DOD. Another thing too, which shouldn't be really a surprise to anyone, so we know kind of the expected value, which seems to be a preferred wind speed rating for DI2 DOD 10 is 200. And so that puts it right at the threshold of EF4 and EF5. And so really, based on this analysis, again, at the highest damage level for residential structures, which is, again, DOD 10, it's probably going to be difficult to accurately assign a true EF5 tornado if we're basing it on actual wind speed greater than 200 miles per hour by residential damage alone. So this kind of initial data analysis is going to help us try to address some broader questions here, going back to some of the motivation in the earlier slides. And so what we're going to do is compare damage to wind speed relationships in the DAT with some existing fragility curves, which is typically used in the engineering space. And so here it's kind of the reverse, where we're going from a wind speed to a damage. And so these empirical fragility curves were built from post-storm surveys with a wind field that's estimated independent of the EF scale. And so basically we go out and estimate the wind field independent of the EF scale, get DOD estimates from just your traditional damage survey to develop these curves. And so really kind of some of the uncertainty in these curves, which I'll talk about briefly, inherently includes some of the damage factors mentioned earlier. All we see is a end result damage state. We really have no idea, unless we're going to do some really detailed forensics, how that particular structure arrived at the damage state. So let me give you just kind of a brief overview of the fragility curve. So for example, on the left-hand side here, so this is kind of 40 meters per second, 90 miles per hour. So if you're looking, if you kind of follow this 40 upward here to, for example, DOD3, what this really tells you is that for 40 meters per second wind speed, there's a roughly 35% chance that the damage state is going to be DOD3 or higher for these fragility curves. And if you kind of continue to move up, this is maybe like around 55% DOD2 damage or higher. And what you can do is you decompose those cumulative functions there in the fragility curves and look at individual damage states for a given wind speed. So here, this kind of tells you the probability for a given wind speed of arriving at a single damage state. So obviously for lower wind speeds, you're going to have the most likely outcome is no damage. And as you move to higher speeds, you're going to get to more extreme damage states for DI2. But another thing I want to point out here is the uncertainty. So take DOD6, right, which is a common DOD for DI2. So it's really the most common, at least based on these curves, the most common damage state for wind speeds anywhere from about 50 meters per second to around 75 meters per second, where DOD6 is the most common damage state. And so we can use these fragility curves to do another simulation that relates the wind speed back to a damage, where the DAT was damaged to wind speed. So we're kind of doing this, what we're calling misclassification analysis. So we can look at potential misclassification of tornado characteristics looking at DI2, and this is really through Monte Carlo simulation. So I have a flow chart here. It might be a little busy, so kind of bear with me as I kind of step through this. So Jim mentioned, so we're kind of taking a number of simulations of a tornado wind field model. So we look at various tornado characteristics, maximum wind speed, radius of maximum wind, path length. We kind of enter this tornado wind field into a kind of simulation space where we're kind of looking at another thing here, which is housing density. So we have various housing densities that we kind of input into this model. You can kind of see an example here of a wind field from the wind field model, and these kind of red squares are houses at a given housing density. And so what we do is we kind of pass the wind field through. If we look at the peak wind speed for a given structure, we kind of run it through this empirical fragility curve model. What it does, it gives us a degree of damage, and then we can use that same degree of damage and simulate a damage-based wind speed through the information that we collected with the DAT. So this was kind of the DOD6 distribution that I showed earlier. And so then what we can do is we can take some of the damage characteristics that we get in the simulation, so the wind speed, for example, estimated from damage, things like damage width, and compare it to kind of our initial values from the tornado wind field model. So things like we can compare the maximum wind speed in the tornado or the maximum wind speed at a house with the maximum wind speed generated from this damage simulation and from the information that we got from the DAT. And so we have some pretty interesting results. We're not going to go into too much detail here because really we wanted to show how we're using the DAT. So for example, the intensity estimation, so this is kind of for a rural density. That's really kind of the focus of this classification, is for areas without a lot of structures. And so this is for all simulated tornadoes. So on the bottom shows the peak wind speed from the tornado wind field simulation. And what we did was basically just ran a bunch of different cases at peak wind speeds associated with values at EF0, EF1, 2, 3, 4, all the way to EF5. And then estimated the peak wind speed from damage using the DAT relationship. And so what we found is that, so if you look at these black dots, these are kind of the median peak wind speeds from damage. For weaker tornadoes, things generally tend to be overestimated. So this is the black solid line, is there kind of the 1-to-1. And as we move up to higher simulated wind speeds, the peak wind speeds from damage then tend to be underestimated. And that should make sense, right, based on what we know about DI2, DOD 10 for in the EF scale, where we're kind of limited on how much, what the maximum wind speed is that you can actually give. And also another thing I want to point out is how much uncertainty there is in the damage. So for a given, let's say roughly 60 meters per second in the tornado wind field simulation, the range of peak wind speeds from damage is large. And so we've looked at a lot of different path lengths, radius of maximum wind. So there's a lot of uncertainty built in based on the tornado characteristics, but wanted to show you one example here. The second thing too is kind of damage width estimation. So this has kind of come out in recent research also, where there's just not enough structures to essentially estimate what the potential damaging width of the tornado is. And so what we did here, this is for EF2 simulated tornadoes, looked at the damage width from the simulation and compared it to the radius of maximum wind. And what you'd hope to see on some level is that this relationship would be more or less the same since you're normalizing it by the radius of maximum wind. But what we find is for smaller tornadoes, essentially, is that it's hard to pick up a path width. And for example, for 25 meters Rmax, which is roughly about 80 feet, the 50th percentile path width is 0 because either it didn't damage any structures in the simulation or just one. So if you're looking at houses only, it's hard to get a damage width. And then here we're kind of normalizing this relationship above by the highest Rmax. So basically 300 meters was the highest that we did in the simulation. We assume that, okay, this is probably a big enough tornado that we're actually kind of capturing the true damage width. There's enough structures in the simulation. And what we find is for different house densities, this is number of homes per square mile. For smaller tornadoes, we're just probably not capturing the potential damage width of these tornadoes, which is obviously going to play into how we estimate tornado risk. And so some findings and some challenges here. From the data analysis, we kind of find two major findings. It's probably not surprising. So one is this kind of empirical cumulative distribution is really a function of DOD that kind of changes as the DODs increase. And then at the upper end of the EF scale, at least for DI2, would really just limit the ability to correctly assess intensity, especially for violent tornadoes. And then in this misclassification analysis, the path width, and we didn't talk about length, but the width is likely affected by the lack of DIs. And obviously we understand that there's other damage indicators out there potentially that you can use, but we focused on DI2 here. And then intensity tends to be overestimated for weaker tornadoes and underestimated for stronger tornadoes based on the relationships that we used here. Now, some of the challenges, and Zach kind of alluded to it when talking about this kind of outlier structures, is accounting for small-scale features in the wind field through damage. So we all kind of recognize the limitations of the EF scale, but if there's some small-scale vortex that affects a structure or two, it may be the best method to try to assess the actual wind speed. But I think we need to kind of sort through some of the factors that may cause a certain damage state. And then again, assessment of small, short-lived tornadoes. We had just a situation here in Champaign where we had 2 EF unknown tornadoes that were small and short-lived on Monday, which are probably more common than we currently know. So those are some challenges kind of in the assessment. And again, some kind of concluding thoughts, and I want to stress this. It's not a criticism of the Weather Service or the surveying process. We understand, we work with the Weather Service a lot. We understand all the challenges that are faced. It's really trying to better understand the wind speed damage relationship and all the factors involved. And the data is really helpful to try to give us an initial understanding of what's going on. Neither method, whether it be the DAT or kind of the fragility curves that we used, is right or wrong. It's just really an approach to try to look at potential ways that intensity and other tornado characteristics can be misclassified. And so obviously the goal is, really develop more objective tools and methods to improve tornado intensity estimation. And, we want to work with the Warning Decision Training Division and the Weather Service to try to do that. And some acknowledgement. So other people in the Wind Laboratory group, in addition to Zach when he was here and now at Haag, Charlotte Poole, Daniel Rhee, and Justin Neville for all their help, and especially the misclassification analysis. And then Jim and Jill, the Storm of the Month team, for inviting us on and giving us a chance to talk about our research. That'll be it, and happy to take any questions or feedback.
All right, I think we're set. So thanks very much, Frank and Zach, for your time. Very informative. And if you have any questions, feel free to email Frank or Zach at a later time. Thanks for your attendance today, everybody, and enjoy the rest of your day.